Section 3.1, Inertial and Non-Inertial Frames of Motion. Think about riding on a bus. While sitting in the bus, based on the sensations that you experience while the bus is moving or not moving, you can almost predict the motion of the bus. You'll feel sensations such as forces pushing you back into the seat when the bus is accelerating forward, or you'll feel yourself moving forward when the bus is coming to rest. And you'll also feel no forces if the bus is not moving, but the same experience can be had when the bus is moving at a constant velocity. When the bus moves at a steady rate, without changing direction, you could close your eyes and possibly not be aware that the bus is moving. If you place a ball inside of the ball does not move relative to the bus. But when the bus slows down, however, you'll see the ball roll forward. When the bus speeds up again, the ball will roll backwards. When the bus turns, the ball will roll to the side. What forces cause the ball to accelerate? The fact is, no forces act on the ball to accelerate it. Let's go over some definitions to help us better understand this section. First, we have a frame of reference. This is a coordinate system relative to the motion that is described or observed. An inertial frame of motion is one at which the object moves at zero or constant velocity. And a non-inertial frame of motion is one at which the frame of reference in which accelerates. And in this case, in a non-inertial frame, the law of inertia does not hold. To explain these various forces, we invent the new idea of fictitious forces. A fictitious force is an apparent but non-existent force that explains the motion in accelerating or non-inertial frames of reference. In the bus example, a fictitious force pushed the ball in the direction opposite the acceleration of the bus. As you continue learning about mechanics, you will encounter other fictitious forces. Fictitious forces simply explain non-accelerated motion in accelerated frames of reference. Let's start with sample problem number 1. A teacher suspends a small cork ball from the ceiling of a bus. When the bus accelerates at a constant rate forward, the string suspending the ball makes an angle of 10 degrees with the vertical. Calculate the magnitude of the acceleration of the bus. In order to answer this question, we're going to make up be positive and right be positive. Since the ball is not moving from this suspended position, neither up nor down, we can state that the sum of the forces in the y direction is 0. Let's draw a free body diagram of the ball. In this free body diagram, we'll use a dot to represent the ball. And we know that there's a force of gravity acting down on the ball. And we know that there's a force of tension pulling up on the ball. The force of tension makes an angle of 10 degrees. And we can break this up into x components of tension, which is tension sine theta, and a y component, which is the force of tension times the cos of theta. Now, since we know that the sum of the forces acting in the y direction is equal to 0, we can add up all the forces using plus or minus to indicate direction. So we know that we have plus the y component of the force of tension minus the force of gravity in the downward direction. Remember, force of gravity is equal to m times g. So in this case, we can rearrange this, and we have the force of tension times the cos of theta is equal to mg. And we can solve for the force of tension, which is mg divided by the cos of theta. Notice I haven't put in any values here, and we're going to use this expression for the force of tension later on. Now, we know that the ball is being accelerated to the left by this fictitious force, and the tension in the x direction balances the acceleration. So we know that, and we'll write this down, the horizontal component of the force of tension Ft sine theta, which I'll just style in blue so that we know it's this x component right here. This horizontal component balances the acceleration. So if we look at the sum of the forces in the x direction, we know that the ball is accelerating and if we list all the forces acting on the ball, we know that mass times acceleration is equal to Ft sine theta. Now, in for Ft, I'm going to write mg cos theta, because we determined up above that the force of tension is equal to mg cos theta. So if we rewrite this, instead of Ft, I'm going to write mg cos theta, mg over cos theta rather, equals ma. We have an m on both sides, so we can reduce this expression so that it's sine theta over cos theta equals acceleration. Forgot to put in my g. G sine theta. And we know that sine theta over cos theta is equal to tan theta. So we can write acceleration is equal to g tan theta. Acceleration is equal to 9.8 newtons per kilogram times the tan of 10 degrees. And if we punch this into our calculator, we get 1.6 meters per second squared. All right. Another common example to study is the elevator example. And we can use the elevator example to determine the apparent weight while in an elevator. You know, when an elevator is accelerating upwards, it feels as if you're heavier. It feels as if you're pressing down onto the ground of the elevator with a stronger force than when it's at rest. So if you were actually standing on a scale while it's accelerating upward, the reading on the scale would increase if you're accelerating upward and decrease if you're accelerating downward. And the reading on the scale is equal to the normal force. Let's write that. Okay, let's calculate the apparent weight of a passenger when the acceleration in this first example is moving upward at 1.5 meters per second squared. So we know that this is an accelerated frame of motion, and in the y direction, if we make up positive and right positive, we know that the sum of all the forces in the y direction is equal to plus ma. If we list all the forces acting in the y direction, we have plus ma is equal to plus normal force minus force of gravity. Now it's critical that when you're studying these apparent weight in elevator questions, that you indicate the direction of the acceleration with the appropriate sign based on your reference coordinates. So if we want to find the apparent weight, what we have to solve for is the normal force. In this case, if we rearrange, bring this over the equal sign, we have the normal force is equal to plus ma minus, or rather plus when we bring it over the equal sign, mg. I'm going to simplify this a little bit. I like to simplify it because you can see that the apparent weight is due to the acceleration of the system plus the acceleration due to gravity. If we sub and solve, 75 kilograms times 1.5 meters per second squared plus 9.8 newtons per kilogram. Notice I didn't change the sign of gravity because I said up here that gravity was negative. I don't need to say it again at this point. It would negate our direction. If you do this, the apparent weight, punch it into your calculator, you end up with 850 newtons, or 8.5 times 10 to the power of 2 newtons. So the apparent weight of the passenger, when it undergoes an acceleration, a positive acceleration of 1.5 meters per second squared, is 8.5 times 10 to the power of 2 newtons. What about when the elevator is moving at a constant velocity? When the elevator is moving at a constant velocity, it's in an inertial state of motion. So inside, the feeling of moving at a constant velocity would be the same as you would experience if the elevator was at rest. So we know in this example that the sum of the forces in the y direction, because it's an inertial frame of motion, because it's at a constant velocity, the sum of all the forces in the y direction would be 0. So let's list all the forces. We have the normal force minus the force of gravity. If we solve for the normal force, we end up with plus force of gravity, which is plus mg, which is 75 kilograms times 9.8 newtons per kilogram. And the apparent weight is the actual weight of the passenger, which is 7.4 times 10 to the power of 2 newtons. This would be the same weight if the passenger was not in an elevator. All right, let's flip the direction of the acceleration, and let's look at when the elevator is slowing at a rate of 0.9 meters per second. So in this case, the acceleration is in the opposite direction. The acceleration is slowing down, it's decreasing. So the net force would be in the opposite direction. We'd have the sum of all the forces in the y direction would be equal to negative ma. So let's list all the forces acting on the object. Again, we have the normal force minus the force of gravity. If we solve for the normal force, we have plus force of gravity minus ma, which is plus mg minus ma. And if we clean this up a little bit, we get g minus a. Let's solve. We get 75 kilograms times 9.8 newtons per kilogram. And the acceleration is 0.9 meters per second squared, or newtons per kilogram. Punch this into our calculator to determine the apparent weight, which is the normal force or the reading on the scale. And we end up with 6.7 times 10 to the power of 2 newtons. All right, have fun trying some of the homework problems in the textbook. Good luck.